Hello everyone, welcome to the week 11 problem solving session for deep learning. So in today's session we will talk about the face recognition system, image denoising system, semantic segmentation aspects and things like that. So let us start with the first problem for today. So the first question that we have is what are the different challenges one face while creating a facial recognition system? Different illumination condition, different pose and orientation of face images, limited data set for training, all of the above. Would anyone like to answer this?
All of the above.
All of the above, yeah, everyone is saying all of the above, that's correct. All of the above is the correct answer. So yeah, there can be different illumination condition depending on where the photo was taken. The person can be in different pose, the camera angle can be different, and most importantly there can be limited data set for training. For example, if we are building a attendance system based on facial recognition in some small company, there it will be difficult to have a very large data set to build this type of system. So limited data set for training is also a issue while doing this while building these facial recognition systems. So yeah, all of the above. The next one, in FaceNet, why the L2 normalization layer is used? So FaceNet, the network that we learned about for facial recognition system, which is a well known network for facial recognition, there why the L2 normalization layer is used? To constrain the embedding in a d-dimensional hypersphere, to for regularization of weight vector, that is the L2 regularization, for getting a sparse embedding function, or none of the above? Yeah, anyone?
Is it first option to constrain the embedding function in dimensional hypersphere?
Yeah, correct. That's the correct option. So as we learnt in FaceNet that the embedding that we want to derive through that network, let's say if it is fx, so there was one constraint that the fx's L2 norm should be equals to 1. That was a constraint that we had while we formulate the problem. We want the representation such that their norm is equal to 1. So to obtain that, we have to put this L2 normalization layer, and when you do this L2 normalization layer, you normalize your final embeddings with this norm equal to 1. So let's say your it can be that embedding can be some d-dimensional vector. So it will be in a d-dimensional space, this embedding, and when you constrain the L2 norm to be 1, you actually constrain all the points to be on the hypersphere. So when you constrain any vector, any d-dimensional vector to have the L2 norm as 1, then basically those come up on the hypersphere in that space. So, when we are putting a L2 normalization layer with which we are normalizing the embedding, we are basically constraining the embedding to be in a d-dimensional hypersphere. We can basically look at it. Let us say if you have a 2-dimensional, let us say 2-dimensional representation. So, we can write this constraint as this square will also be 1, right. So, if it is a 2-dimensional representation, let us say x1 and x2 are the 2 dimensions, and let us say so this x1 x2 are basically I am saying let us say I denote it as f1 f2. This fx is basically I am saying a 2D representation, and the 2 dimensions are f1 and f2, let us say. So, if we constrain this condition, that means what we are making f1 square plus f2 square root, that is the L2 norm, that square should be equals to 1. So, that means your f1 square plus f2 square should be equal to 1, which is the equation of a circle in 2D. So, if you are in a 2D and you constrain your feature or your vector to have a unit norm, L2 norm, then you are basically having your data point such that it lies on a circle. So, in 2D it is circle. If you generalize it into higher dimensional, let us say in D dimension, so in 3D it will become a sphere, in D dimensional it will become a hypersphere. So, whenever you restrict the L2 norm by 2 1, you are basically restricting it on a hypersphere of radius 1. You are restricting the embeddings to be on that sphere. If it is some other norm, then based on that the hypersphere dimension will be the radius will be different depending on that. Okay. Yeah. So, the L2 normalization layer basically constrains the embedding function in a d-dimensional hypersphere. Correct. Moving on to the next one, here we have 2 statements. We have to say which one is correct, which one is not, or both are correct or both are not. So, in the context of triplet loss for face recognition, hard negative example is just a minute. In the context of triplet loss for face recognition, hard negative example is whose embedding is far from the anchor and belongs to same person as the anchor. And statement 2 is in the context of triplet loss, hard negative example is whose embedding is near to anchor but belongs to a person other than the anchor. So, we have to say which one is true, which one is false. I got answer. Pooja is saying 2. Statement 1 is false, statement 2 is true. Anyone else?
Yes, option 2 is right.
Yeah. Okay. Yeah. So, basically negative example means it is not same as the anchor person. This data point belongs to some other person than the anchor person. So, and basically if it is hard negative because it is closer to the anchor point, but it is actually from a other person, that is why it is hard negative. And positive examples are basically the examples which are same which are for the person same as the anchor, and for them hard positive will be actually the ones for which the embedding is far from the anchor, but it belongs to the same person. So, for the first one is basically the description that is given, that is not hard negative, that is actually hard positive example. Moving on to the next one. Fully connected convolutional network or FCN became one of the major successful network architectures. Can you identify what are the advantages of FCN which makes it a successful architecture for semantic segmentation? larger receptive field, mixing of global feature, lesser computation, or all of these. Anyone? Any answer from anybody?
Maybe one.
You are saying one, larger receptive field. Okay. Any other option? Or is everyone agreeing with option 1 only? Okay, I'll tell you. So this is basically all of these three are the advantages of FCN. The correct answer is all of the above. Larger receptive field is of course one of the advantages. This FCN uses strided convolution with stride more than 2 or more than 2. So its receptive field is larger. Also it does mixing of global feature. So when you upsample your label map, then you take your upsampled version and you also take the feature at the output of some previous pooling layer which is at the same dimension or same resolution, and you add all of those two and again upsample those. Again for FCN 8s you actually take one more step like that. You use that skip connection and you take the feature from a previous pooling layer and add it with your upsampled feature, and again after combination you again upsample that. So that mixing of features is actually happening here, and that actually helps in doing better upsampling that we have seen. If you just directly, so in case of FCN we have to upsample our label map by 32x upsampling has to be done. So if you just do it in one step you get a very coarse output, but when you are doing 16s, first you upsample by 2 times 2x and you add the previous pooling layers output also, and then you upsample by 16x, and then you can do this one more time and you can get the 8x. So in these cases we have seen that the output is better. So because of mixing this previous feature we actually introduce those finer information into our output label, so that actually helps. So this mixing of global feature is also an advantage of FCN, and lesser computation is also an advantage because you are doing strided convolution. So your feature dimension is reducing and you have to deal with lesser number of parameters, lesser number not parameters actually, lesser dimension of the data as you go on reducing your feature dimension. So lesser dealing with lesser dimension also means that lesser computation is involved. So because of this strided convolution you are actually getting this lesser dimension and lesser computation. So that is also an advantage. So all these three are basically advantages of FCN. So the correct answer is all of the above. Next thing is, those were the advantages. What is the disadvantage? So the first option is it has a fixed receptive field. So, the object with lesser size than the receptive field will be missed. Downsampling the image dimension over the depth makes the feature map sparse, or it requires a lot of computation, or none of the above, which is the disadvantage of FCN.
Ma'am, in the previous question, I have a doubt actually.
Yeah.
The semantic segmentation is normally actually it is producing high resolution image, no?
Yeah, same dimension
But
as
how the computation is the third option, no, lesser computation, how it is happening?
So when you are doing you have multiple layers of convolution layers, right? Multiple convolutional layers, so each, and pooling layers also. So the output of each, at the output of first you are getting half of your initial dimension, then say 1/4 of your initial dimension, 1/8, like that. So if you just had the dimension same as the input image, that would require more computation than having this downsampling at each step. So because you are downsampling, the dimension that you are dealing with, that is reducing. So your each multiplication, addition, the matrix multiplication and all, those dimensions are less. So in that way it is requiring lesser computation as compared to having the entire image put together. I mean,
But the reverse process also happening, no, ma'am, in that link.
Yeah, reverse process is also happening, but think like so in case you didn't have those downsampling, you just had convolutional layers with just stride of 1, and so there was no reduction in the dimension of your image, then you will have to do more computation, right? You will have to so where now at the output of the first pooling layer you have got, let's say, half the dimension of the input image. Instead of that, if you do not do that downsampling, you will have the initial image dimension only. So there itself you will have more computation involved instead of having this downsampling. So downsampling actually is reducing the image dimension for the till the convolution part. So for the deconvolution or the upsampling part, you will again have to go back, that's there, but for the convolution part also it is reducing the computation, because it is reducing the dimension.
Okay, thanks, ma'am. Okay.
Yeah, anyone, the disadvantage? Okay, so there are 3 options. It requires lot of computation, that's not of course the disadvantage, because we just said it has the advantage that it requires less computation. So option 3 is gone. Option 2 says downsampling the image dimension over the depth makes the feature map sparse, but again we are introducing those skip connections and again having the finer information back. So actually the disadvantage that we have is this thing. The FCN has a fixed receptive field, so the object with lesser size than the receptive field will be missed by the network. So basically when we use FCN, we put the entire image as a whole to the network, and based on your stride and kernel size, your some receptive field will be there, that is also fixed. So if your receptive field is much larger than the size of your actual object, then that might be treated as some background or foreground. Or if your receptive field is too small as compared to your object, then you are just getting a part of the object, that's also not the correct way of doing it. So that's the actually advantage. So this deconvolutional network that came after this FCN, those actually handled these this disadvantage. So what they did is they do not take the entire image as a whole to the network, they actually divide it into several smaller segments which they call different instances of proposals. So for each segment they do the entire convolution deconvolution thing, and obtain a label map and combine all those small segments together to get to the final label map for the entire image. So, because they are not giving the entire image as a whole, they are based on the receptive field, they can choose what portion of the image they want to put it, what should be the segment size of that image. So, that receptive field is much larger with respect to what object you want to detect, or much smaller with respect to the object. Those things do not happen there, but in case of FCN, that's a problem, because you give the entire image as a whole. Okay. I hope that is clear to everyone. Moving on to the next question. What is the use of skip connection in image denoising networks, or in any network? What is the use of skip connection? Helping deconvolution layer to recover an improved clean version of image, back propagating the gradient to bottom layers, which makes the training easy, to create the direct path between convolution layer and the corresponding mirror deconvolution layer, or all of the above. So, what do you think is the use of skip connection in an image denoising network? Let's see. Anyone? No guesses from anyone? Jyoti is saying option 1, which is helping deconvolution layer to recover an improved clean version of image. That's of course one use of skip connection, but that is not the only use. All three options 1, 2, 3 are actually correct, and your correct option is all of the above. So, when you have skip connection, that of course helps the deconvolution layer to recover an improved clean version, because otherwise when you do multiple convolution, you actually at the very deeper layers you actually lose the finer details of the information, because your receptive field keeps on increasing. So, you keep on losing, and you also do the pooling operation in between, that also loses some information, some detailed information. So, you keep on losing the details. So, during deconvolution, if you just use the final output of the convolution portion, then you do not have access to those finer detailed information. The skip connection, when we use, we actually take the feature map at some lower less deep position and add it to the deconvolution layer output. So, that actually helps in getting those finer information in our clean version of the image. So, actually it helps to recover an improved version of the image, but it also helps in back propagating the gradient to bottom layers, which makes the training easy. So, we talked about this vanishing gradient problem, right? When we have a very deep network and activations like sigmoid, tan H, those things, then you can have vanishing gradient problem. So, when you are using this skip connection, so one connection you have through this normal through convolution layer, through deconvolution layer, but along with that you have one more connection that is going like this. So, your gradient will flow this way normally, but it will also flow this way. So, from here it directly grows to here, it do not need to go through all these layers. So, So in turn the chance of your gradient becoming very small, or chance of you having the vanishing gradient problem becomes lesser. So you can have your gradient passed to the initial layers or bottom layers of the network easily, and since that helps in keeping your gradients, that helps in not letting your gradients become too small, or that helps in overcoming the vanishing gradient problem. So it helps in the training process also. And last is to create a direct path between convolution layer and the corresponding mirror deconvolution layer. So the corresponding layers have a connection between them, so it gets that information, that finer details that was lost. So all these things are actually some uses of having the skip connections. Okay, if you have any doubts, anyone up to this point, you can just post it or just unmute and ask. I'll pause for 1 minute and I'll move forward after that. Okay, let's move on. This is the next one. Which of the following, I hope the writing is clear to everyone, it's a bit small font because of all these options. Which of the following can be a target output of semantic segmentation problem with 4 class? So you have a semantic segmentation problem where you want to detect 4 different classes of objects. In that case, the target output that you need to provide for supervised learning. So what is a possible combination for that target output among these 4 options? Which one do you think can be a valid target output for semantic segmentation? Any guesses? So first let us see how our target output should be for semantic segmentation with 4 class. So generally when we have 4 class classification problem, let's forget about semantic segmentation. First let's say we have just a classification problem where we have 4 different classes. In that case, what will be our output? Target output will be basically your class level, whether it belongs to class 1, 2, 3 or 4. And so let's say that class level is 1, 2, 3 or 4, but you cannot directly give that 1, 2, 3 or 4 as your ground truth value, right, or target output value. You have to convert it into one hot representation. So if it is a 4 class, you have a 4 dimensional vector, and the class to which that data point belongs, that particular dimension will be 1, otherwise it will be 0. So that's basically the one hot dimension. So let's say your example belongs to class 1, then you will have one hot representation like this. So, you have 1 at the dimension 1 of your 4 dimensional vector and 0 otherwise. Now, if it is class 3, you will have something like this. So, for classification, this is how your target output should be. So, it should be 1 hot encoded. Now, in case of semantic segmentation, what it basically is, we are basically trying to classify each pixel as one of those 4 classes. So, it is basically a classification problem only, but the classification is happening at the pixel level. So, each pixel we are classifying. So, if there are 4 possible classes, then for each pixel can belong to any of those 4 classes. So, for each pixel your target output should be this type of a 1 hot encoded vector. So, let us say you have 4 classes, that means for each pixel location you will have a 4 dimensional target vector, and here as you can see these 1, 2, 3, 4, these are basically the 4 dimensions, and this matrix is basically the xy coordinates of your image. So, this is basically your image is 0, 0, 0, 0th pixel, this is your 0, 1th pixel, like that, and you have 4 dimensions for each pixel location. So, all these are corresponding to 0, 0, right. So, these 4 elements all are corresponding to the pixel 0, 0. So, this 4 dimensional target vector is will actually tell what is the target class for the pixel position 0, 0. So, these 4 0, 0 position taken together, if we form that as a vector, that should be a 1 hot encoded vector, because any of the pixel can belong to any one of the classes, right. It cannot belong to 2 or 3 of the classes at a time. It will be either a cat or a dog or something like that. So, among these 4 values that I have marked as 0, 0 pixels corresponding 1 hot target vector, only one of those values can be 1. I will just erase this for better visibility. So, so this vector has to be 1 hot encoded. So, this vector has to be 1 hot encoded, that means only one of these 4 values will be 1 at each pixel location. So, what do we have to check? We have to go at each pixel location. Let us say we want to go to 0, 0. So, we have to check the 0, 0th value of all the 4 matrices, and if only one of them is 1 or among these 4 0, 0th values of the 4 matrices, then that is a valid a valid 1 hot representation. And if we have valid 1 hot representation for all the 9 positions that we have, all the 9 pixel positions, then it is a valid target output. So, here first option I got from Jyoti, which is D. So, if we see D, let's see if it is a valid one. So, let us first take the 0, 0 position. So, 0, 0 position, here it is 0, 1, 0, 0. So, first position it is correct.
At the second I think repeat. So, D may not be there because it is 2, 4, 4 again. But then there is second row.
2, 4, 4 what?
I mean the decimal equivalent, no? Second row.
Second row. Yeah, these two you are saying, right?
Yeah. That not match.
So, this is not a valid position for the second row first column position, that is not a valid 1 hot vector. So, it cannot be the target output. Another option I saw from Yashas, which is option C. So, if we let's take some examples and let's check for the 0, 0 position. It's
no, that
1.
Can also not be there. Third row is same for I mean the third row is 1, 1 for 2.
1, 1.
I mean 0, 0.
For
second and third is 0, 0. No.
0, 0 is fine, right? Both can be 0. That's not an issue. So, you just since your each pixel can belong to just one class, among the 4 only one element can be 1. So, So, each of your pixel will belong to one of the 4 classes. So, if you just take this, you have to compare these 4. So, only one of these should be 1. 0 will be multiple, of course, 0 will anyway match, many of them will be zeros. So, yeah, of course, C is actually the correct answer. If you check all the elements, you will see that at all positions only one of the 4 matrices are becoming 1. I mean, I guess I get your point. So, there might be some positions. Okay, let me see. That's fine. Yeah, yeah, fine. So, if you just check the elements, all the 9 elements, 9 positions, you will see only one of the 4 matrices are 1 at those positions. Nowhere you will get that 2 matrices have 1 at the same position. But if you check option A, let's say, you see here at the same position you have 2 ones. So, it cannot be a valid target output. For option B also, you will see, you have 2 ones at the same position. So, that also can't be a valid target output. So, the correct option is C, where for each pixel location we have a 1 hot vector as the target output, and each 1 hot vector is a 4D vector in which only one element is 1. So, that is how your target output should be. Okay. Now, moving on to this one. Suppose you have a 1D signal x, what is just a simple signal 1, 2, 3, 4, 5, and you have a filter f 1, 2, 3, 4, and you perform stride to transpose convolution. Transpose convolution is basically deconvolution on the signal x by the filter f to get the signal y. Now, you have to tell what will be the signal y if you do not perform cropping. So, we are not considering that we will crop and all, we will just take the entire output that we get at the initial just after doing the transpose convolution or deconvolution. So, let us see this one. So, the signal that you have is 1, 2, 3, 4, 5 and your filter is 1, 2, 3, 4 and you are doing stride to convolution, right. So, let us write your signal at the top, which is 1, 2, 3, 4, 5. These are the signal values at the 5 positions. Now, for doing deconvolution, what you do is below each, starting from the first position of your signal, you write your filter coefficients vertically below this number. So, your filter coefficients are 1, 2, 3, 4. I will write 1, 2, 3, 4 just below the first position of our signal, or if we say it as x0, x1, x2, x3, x4. So, below x0 we write our filter in the vertical direction 1, 2, 3, 4, one below the other. Now, going to the x1 position, you have stride to deconvolution. So, you will have to move your filter by 2 positions. So, you will have to move it 2 step down. So, now your filter will be placed here. Again, going to x2, same thing you have to do, again move it 2 step down. So, you will have 1, 2, 3, 4, again 1, 2, 3, 4, again 1, 2, 3, 4. So, with that we have covered the entire signal. Now, how do you compute the output signal? So, for computing the output signal, now you basically consider each row at a time. So, if you consider the first row, this is the coefficient, and with this coefficient you will multiply the corresponding position's signal value. So, here you just have one coefficient just for the position x0. So, you will just multiply 1 into x0, which is 1. So 1 into 1 1, which gives the first element of your output signal y. Now you will do like this for each row. So for the second one, again you just have one coefficient, so 2 into x naught x 0, which is 2. Now here you have two coefficients. So what you have to do? You have to do a linear combination. So 3 into x 0 plus 1 into x 1, 3 x 0 plus 1 x 1, like that you have to combine. So here you will get 3 plus 2 5. Similarly for this one you will get 4 plus 4 8, 4 plus 4 8, like that you have to compute the entire thing. So let us just complete the calculation. In the next row we have 3 into x 1 plus 1 into x 2, which is 6 plus 3 9. Then we have 4 x 1 plus 2 x 2, which is 8 plus 6, which is 14. Then next we have row x 1 column is complete. So no more contribution from x 1. Now we have contribution from x 2 and x 3. So now it is 3 x 2 plus 1 x 3, which is 9 plus 4 13. Next is 12 plus 8 20. Then now contribution of x 2 is completed. Now we have just contribution from x 3 x 4. So now it's 12 plus 5 17, then 16 plus 10 26. Now we have contribution from only x 4, x 3 is also complete. So we have 15 20, last two rows. So the final signal that you have is basically starting from here. This will be your starting of the y signal. So here we are not doing the cropping. If we do cropping, then this initial and end elements will be cropped out, but otherwise since we are not doing cropping, the signal that we will have at the output of transpose convolution is 1 2 5 8 9 14 13 20 17 26 15 20, right. So if you see our question, this is basically option C. Option C.
Ma'am, I have one question.
Yeah.
If here we perform cropping, then what will be our answer?
So if we perform cropping, so here actually, so your this kernel is basically positioned at the, let's say first you will position your kernel at y 0, centered at y 0. So if you center it at y 0, this has equal number of elements, so you can consider this also. Maybe depending on what convention you use, you can either if you use this will be my position where I consider the filter is placed. So your start should be from here. So the first element will be cropped out. But if you consider this as your starting position, then both the first two will be cropped out. Your start will be from here. So depending on what convention you use, that depends on the choice. So depending on that, you will either have to crop out one or both 1 and 2.
Okay.
Also at the end also will same thing will happen, because here if you consider the second position as your center point, so last your center point is at here, so your signal will come till this point, from 2 to this point, or from 5 to sorry, not here, 5 till 15. So if you consider this, or maybe I'll use some color, let's say. If you take the second position, then your signal starts from here and it goes till here. If you take the third position as your center point of, or where the filter is placed, then your signal is basically from here to here. I hope that's clear.
Yes, ma'am.
Let us move on to the next one. So now the question is, in a deep CNN architecture, the feature map before applying a max spool layer with 2x2 kernel is this. Now after this max spooling, you have done successive convolutions and the feature map is again upsampled using max unpooling. Now before the max unpooling layer, this is the feature map present before max unpooling. Then what will be the output of the max unpooling layer? So if you do max unpooling on this matrix, what will be your output? So we know when we use this max unpooling layer, so we basically while doing the pooling operation, we basically store the positions of the maximum elements. So if here we are doing max pooling, so we will store the position of the element which is the maximum in this kernel, and we will use that position to do our unpooling. So while doing the max pooling, this matrix is just before the max pooling. So you will basically you are using a 2x2 kernel, right? So first your kernel will be placed here. Kernel will be placed here. The maximum value is 19. So your max spool output will be 19, but you will store this position in a matrix. So you will keep a record like this. So when my kernel is at the first position, then this was the position or the index where I had the maximum value. Next it's a stride 2 so here since you are doing downsampling, so it's basically it has to be stride 2 to reduce the dimension. Now if you put it here, then your maximum is 18. So your this output will be 18, but in the position mask you will keep this, because this position is the one which gave you the maximum value in this placement of the kernel. Then you will put your kernel over here, then you will get 1 0 0 0, and in the last position you will get 0 0 1 0. Then you have here, and the outputs you will get 14 and 19. So this is basically your position mask that you have for the max pooling. Now when we want to do unpooling, you will have to make use of this position. So what we basically do is, this 5, this we got from the first position of the kernel, first placement of the kernel. So when the kernel was here, corresponding to that output, now we have got this 5. So if you want to do unpooling, first we will place this 5 at all those points which the kernel covered. Similarly 6 we will put at all those points where the kernel was at the second position, or when it was like this. Similarly we will have 8 8 8 8 for this position, actually, and 13 13 13 13 as for the fourth position. Now this matrix and this matrix we element wise multiply. So if you do that multiplication, what you will get? You will basically get 0 0 0 0, because your first row didn't have any maximum values. Then you have 1, that means 5 0 0 6, then 8 0 0 0, then 0 0 13 0. So this will be the output of your max unpooling. So basically you can, so I showed you the entire step of how this is implemented, but for giving the answer you can directly put each of these elements at the corresponding maximum positions. So you can directly write based on this position mask. So for the first element, this position is the highest, so you put 5 at this position. Then for the second element, this position is highest, so you put 6 at this position. For third element, this is the point where you should put, and the fourth element you should put here of the matrix. So you can directly, using the position mask, we can say what will be the output of the max unpooling there. Okay, is it clear or any questions?
Yes, ma'am.
Let's move on. The next question is on about dice coefficient. So here you are given two one-hot encoded vectors A and B, and you have to compute the dice coefficient for this, and for the cardinality you should consider the number of bits which is equal to 1, that should be the cardinality. With that you have to compute the dice coefficient. So can anyone compute and tell me the answer? Seven by 14 plus 5 by 14. Okay, but that's not the correct thing. How actually are you computing this? So let's first see what is the formula for dice coefficient. The coefficient, I'm writing dice coefficient as DC. So the formula is 2 into cardinality of the overlap A intersection B, which we basically compute as the element wise multiplication between A and B, divided by the cardinality of A plus cardinality of B, right. This is the formula for your dice coefficient, right. So here for cardinality we are taking the number of 1 bits. So in A the number of 1 bits is 1 2 3 4 5 6 7. So cardinality of A is 7. Cardinality of B is 1 2 3 4 5. Cardinality of B is 5. Now A intersection B, which is basically element wise multiplication. So this element wise multiplication will be 1 only at those places where you have 1 in both the both A and B, right. So that cardinality will basically become the number of position at which both A and B are 1. So that is 1 here, 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 4. So cardinality of A intersection B is 4. So if you put that, so you have 2 into 4 by 7 plus 5. Yeah, this will, if you compute, it will become 0.67, which is option C. Yeah, Jyoti, 8 by 12 is actually the correct answer. Okay, now another one for dice coefficient. For this, what these are the A and B matrices, and here we have to consider the cardinality of A as the sum of all elements of A. So here we have to, so as I saw, we have to compute cardinality of A, cardinality of B and cardinality of A intersection B, right. So can somebody please compute the cardinality of A? Can anyone compute this please? The cardinality of A, which is basically the sum of all the elements of A. Okay, I'll just write the value for now, you can just verify it later. The sum of all the elements of A will be 7.82. So cardinality of A is basically 7.82. Cardinality of B, again sum of all the elements, so here we have just 8 ones, so our cardinality of B will be 8. And for cardinality of A intersection B, so what will be the A intersection of B? You just element wise multiply, so all these two rows will become zeros, so you don't consider these two, only these two will remain because these will be multiplied by this one portion, the top row two rows will be multiplied by the 0. So you just have to take the sum of these elements as the cardinality of A intersection B, that will actually amount to 7.41. Okay. Then again the same formula, so you will have 2 into 7.41 by 7.82 plus 8, which basically becomes 0.94. So this is how you compute dice coefficient. Now when we use dice loss, that is basically 1 minus the dice coefficient, so then the dice loss will be 1 minus this 0.94 for the, if these are the predicted and ground truth matrices. Okay. Let us
So calculator will be provided, ma'am?
I guess some on-screen calculators will be there most probably.
Okay.
Yeah. So the next one, these are the next last few questions I have are from the this week's assignment. So we'll just go over these once. So here it is saying again two statements, which one true, which one false. pixel wise cross entropy loss can be used as cost function for semantic segmentation, and KL divergence loss can be used as cost function for instance segmentation. So, which one or both do you think is correct, or both are wrong? What will be the answer for this, anyone?
One is two, ma'am, but don't know about second.
One is of course true, pixel wise crop. So, semantic segmentation is basically pixel wise classification task. So, pixel wise cross entropy loss will be the cost, can be the cost function for semantic segmentation. So, in case of instance segmentation, KL divergence is not the loss that we use for instance segmentation. So, instance segmentation is actually one step ahead for semantic segmentation, right? In semantic segmentation, all the instances belonging to one class, you mark those as the same label. But in case of instance segmentation, you separately mark each of the instances. So, actually there is a state of the art network for this, which actually does semantic segmentation as well as boundary detection for each of the instances of each class, and it actually minimizes the loss for both of these operations and combine the two finally. So, from the semantic segmentation, it will get the entire portion of the image belonging to one class, then within that it will put boundaries around each of the instances. For that, it will try to find the bounding boxes of each of those instances. It will try to minimize the error in detecting those boxes. So, for the semantic segmentation part, again pixel wise cross entropy loss I guess is used, and along with that you will have to have some loss for the boundary also. So, KL divergence loss is not the one that is used for instance segmentation. Only statement 1 is correct here. Next one, instance segmentation treats multiple objects of the same class as a single entity. Semantic segmentation treats multiple objects of the same class as distinct individual objects. So, I have just now said the answer. So, anyone?
Option 4.
Option 4, both are false. Correct. Actually, it's the opposite. Semantic segmentation treats multiple objects as single entity, and instance segmentation treats multiple objects as distinct individual objects. Correct.
Yes.
Moving on to the next one. Next one says semantic segmentation can be considered as pixel wise classification problem. Semantic segmented output has same dimension as the input image dimension. Now, which one is correct? True.
Statement 1 is correct.
Okay. What about statement 2? So, if you do pixel wise classification, for each pixel you should have one classification output, right?
Yes.
So, for each pixel you should have an output. So, in the input, as many pixels as they are there, in the output that same number of labels should be there.
Yes.
So, your output dimension and your input image dimension should be same.
Okay.
So, both the options are actually correct. I mean true. Now, this one, which of the following operation does not increase spatial resolution of features? Max unpooling, deconvolution, pixel shuffle or average pooling? Option 3, pixel shuffle does not increase spatial resolution. What
Option
about option 4? Okay.
Average pooling.
Average pooling, yeah, average pooling do not increase the spatial resolution. I got this answer option 3 from Penelope. Actually, Penelope, this pixel shuffle is basically same as the subpixel convolution, where you just put 1 0 between each pixels. So alternate position, you just put zeros and you increase the dimension and then you do deconvolution. That's basically pixel shuffle. So that also increases the spatial resolution. That's one way of doing the deconvolution, which is the subpixel convolution. So that's what pixel shuffle is basically. So it indeed increases spatial resolution. Deconvolution also increases max when pooling, to we just sometimes before saw that it actually increases. Average pooling is the only case where you reduce the spatial resolution. The last problem is which of the following operation does not reduce spatial dimension? Does not reduce spatial dimension. Max pooling, two types of convolution, all other things same, stride 2, stride 1, and last is average pooling. What should be the correct way of not reducing your spatial dimension?
Option 3.
Option 3, yeah, correct. So max pooling, average pooling, both are pooling, so they will basically reduce your spatial dimension. And convolution also, when you use stride 2 or more, then you reduce your spatial dimension. If you use stride 2, you basically half your dimension. Oh no, sorry, for pooling, if you use stride 2, that's half of your dimension, not for convolution. You have to compute, but indeed the spatial dimension will be reduced if you, so let's say this is your signal and you have I'm just doing it 1D, though they are saying it is 3 cross 3 kernel, so it's a 2D. I'm just taking the 1D counterpart. So let's say it's a 3D kernel. So first you put it here, then your stride is 2, so you move it 2 positions, you put it here, then last, let's say this has one more, so last you put it here. So from this you get one value, from this you get another value, and from this you get another value. So initially you had 7 values, now you have only 3 values. So stride 2 basically reduces, but if you use stride 1, okay, you also have padding. So if you have padding on both sides, then it should be slightly. So it was your initial, you have padding of 1 on both sides. Now if you do with stride 2, these 3 will give the first value, with stride 2 these 3 will give the second value, again these 3 will give the third value, and these 3 will give the last value. But if you do with stride 1, so this is one value, then this is the second value, so these 3, then second, third, fourth, fifth, sixth, seventh. So before padding, the initial signal was 7 values. Now after doing the convolution with stride 1, again you have 7 values. So your dimension, spatial dimension do not reduce when you use stride 1 as compared to stride 2, where it actually reduces. Okay, so these were all the problems I planned for today. If anyone has any doubts at this point, we can discuss that, then we'll close the session for today. what is DL convergence? DL in the sense, do you have a full form for DL?
It should be KL, ma'am, I think.
Oh, not convergence. It's scale divergence actually. This one, right? So this one you are talking about, yeah. So yeah, this is not convergence at all, it's divergence. So KL divergence is basically a measure of difference between two distributions. So when you want to do a distribution comparison, let's say two distributions are same or not, that kind of comparison you want to do, then we do not generally go for MSE or something like that. In that case we compute the KL divergence between those two distributions to actually see how similar those two distributions are. You can just check the formula for this. So I do not exactly remember, but the formula will be something like from one distribution, let's say if it is Px, then Px log of Qx by Px or Px by Qx. I will not write this, I don't actually remember this. So something like that, Px log of Px by Qx or Px log of Qx by Px, sum over all x values. If you take that, basically gives you a measure of how close two distributions are. That is what KL divergence is. You can just check the formula, or maybe I will check it. Yeah, whatever I wrote that was correct only. So the formula is summation over x if you do Px log of Px by Qx, where your Px and Qx are basically two distributions evaluated at the x points. P is one distribution and Q is one distribution. You are just taking the you want to just measure the similarity or dissimilarity between the two. That measure is KL divergence. It's basically, the full form is Kullback-Leibler divergence. Okay. Any other doubts?
So there will be no more session, online session, ma'am?
One more will be there from my side, one more will be there next Saturday, that will be the last one.
Okay.
But for
And,
other days, I guess next Tuesday also, this Tuesday and next Tuesday will have sessions.
Okay. And for exam, only they should prepare or all assignments?
Exam, I guess, I mean, it can be anything from whatever was taught. I just did some questions that kind of covers the entire part, but yeah, I mean, anything, any theory or something
It's
can
a
come.
very heavy subject.
Yeah.
So many things you have to remember.
But yeah, if you get the idea, I guess most of the, if you have the concept, I guess most of the problems will be able to answer.
Okay. Okay. Thank you.
Any other doubt from anyone? Okay, if there is no more doubts, then we'll close today's session here. Thank you everyone for joining. We will have the last session next Saturday. Thank you guys.
Thank you, ma'am.